3-5. Kinetic molecular theory. Kinetic means what? Movement, motion, okay? So remember, all molecules, all substances are constantly moving, okay? Some of them are in fixed state, and they're just vibrating back and forth. Other things are able to flow past one another because their intermolecular forces are weaker. And then other things are able to spread out really far. I'm going to move this, and then it's going to pop away, and then we're going to bring it right back. Okay. So kinetic molecular theory then is a simplified model. It's going to explain the nature of gases. It's based on a few things. The size of the gas particle is so small compared to the distance between the particles, and the volume of those particles is negligible. So the volume of the gas can oftentimes be ignored, at least for this theory. So gas particles are in constant random motion. They're moving in straight lines. They will bump into each other, and they will collide and bounce off of one another. They'll also collide with the sides of the container. The collisions with the sides of the container that they're in is what we can measure that, and that's your pressure. That's your gas pressure, okay? We can also you can kind of think of the earth as a container, okay? So we actually have pressing down on us all the time a certain amount of gas in our atmosphere. Okay? You go to other planets like Mars or other places where they don't have an atmosphere and there's nothing pressing down on them. So and that pressures, they actually measure that in weather, and they look at different pressure fronts. And if you take earth science, any kind of earth science class, a lot of times they'll get into that. My oldest, that's the pilot, he had to do a lot of that when he was going through aviation, and learning about that type of thing. Okay. So particles are assumed then to have no attractive forces. We call those ideal gases. Now, in the real world that we live in, there may be some of that attractive and repulsive stuff there. But when we're doing our math here, we're just going to assume that that's not in there. It's kind of like in physics where you assume that everything's in a vacuum or something like that. It just makes the problem so much easier. Okay. When you get into college and kind of your more advanced courses, then they'll start taking that stuff into effect, and then life gets eerily difficult. And but you need more math and that sort of thing in your background to be able to handle it.
Excuse the interruption. Will the following students please report to the J room immediately? Grace Adams, Kayla Brown, Alex Curry, Nicole De La Mora, Louis Falligant, Rosalind Johnson, Ruby Lynn Johnson, Faith Kettle, Zofia Lencho, Jacob McCluskey, Braylon Schleiger, Bryn Sikich, Noah Sukrich, Zitavius Williams, Grace Zass. Please come to the J room.
Noah's a junior. Yeah, and he was the rock star of AP Chem last year. Every year I have a kid that I typically, like, if I'm doing something new and I want to check an answer key, I'll start with that kid's paper. That was Noah last year. So anyway, average kinetic energy of a sample then is proportional to the temperature in Kelvin. So the kinetic energy is 1/2 mass times velocity squared. I've never seen where we've actually had to use this equation on the exam, but it's good to kind of have in your back pocket and be aware of. Okay? All right. Again, we've talked about these different laws, different things, and we can kind of look at them and see how they apply to one another. So if your volume is decreased, your pressure will increase. Okay. And this, when they talk about volume here, when they use this V, they are talking about the volume of the container. Okay. People oftentimes will get the volume of the container and the volume of the gas. They'll kind of like confuse that, like the amount of gas in there. They think that the amount of gas is the volume of the gas, and they're not. The amount of gas is going to be in moles. They're going to do that with N. Okay. Now, that amount of gas, whatever it is going to take up whatever volume it's given. So it will spread out as far as it can for whatever whatever volume is available for it. Okay. So the volume of the container is always assumed to be the volume of the gas. So when they give you the volume of the container and you're like, well, I don't know. Or when they give you like multiple gases and they only give you the volume of the container, people are like, well, this gas will take up this spot in the container and this gas will take up this spot in the container and that'll be its volume. No, it's going to spread out as far as it can. All the gases will spread as far as they can. So assume, even if you have multiple gases in there, it's still going to be the volume of the container. Make sense? Okay. We did all of these different laws back in regular chem. None of these, I do not believe, are on your formula sheet. No, none of them are on your formula sheet, but you might want to, have them available. I guess that kinetic one is this formula is on the formula sheet, the kinetic energy one. So it's fair game. They could make you do problems with it. I've just never run across any of them. All right. This is always on there in some form, either a multiple choice question or a free response. I don't believe that I've ever seen a year go by that they haven't quizzed you on some aspect of this Maxwell-Boltzmann curve here. Okay. It's going to show you the distributions of those kinetic energies. At the origin here, it's assumed to be 0 for the speed. So that's down here. And if you have a colder gas, it makes sense that colder gas is not going to move. Is not going to move as much. So this is your colder gas here. It's not going to have as much speed as something that's at room temperature or something that is a very hot gas. The very hot gas is going to have more particles that are going to end up being in that hot area. Okay. You will see these Maxwell-Boltzmanns on there. It will be somewhere. I would put money on it. Yep.
How does the number of molecules change for gas?
How does the number of molecules? Okay. So if I had more cold gas here, is that what you're asking? I would probably have an arc piece of junk. I hate this thing. Why can't it just work the way I want it to? Lord, it skipped back to good grief, back all the way to the beginning. Okay, let me pick up my marker. Maybe it'll work better. Let's say that I had fewer molecules of gas, because that'll make a little bit. I'm going to have, it would probably be more of an arc like that. Okay, because I wouldn't have, this is number of molecules over here. Okay, so if I had fewer, they would still have about the same average speed here. So average speed would come right here for that molecule. Okay, I just wouldn't have as many of them. Where did my line go now? So I just wouldn't have as many of them, because that's what this axis is about, is number of molecules. Good?
Yeah.
Okay, you got another question on it, or is it making sense?
No, it kind of makes sense.
Everybody good? Okay. Yeah, I would not be surprised if you didn't see one of these on there. All right, so, well, increasing the temperature of it is going to change this. So I guess, yeah, I was still right with that being average. This one just has an up and a here. So this is number of particles at speed. That's speed 2. So they're increasing the temperature here. So they increase the temperature. The most probable speed would be here because you got the most molecules there. So that makes sense. And then this distribution, this isn't a Maxwell-Boltzmann though. Maxwell-Boltzmann is always this bell jar kind of looking thing here. Bell curve. We call these bell curves because you can kind of imagine a bell, like the ding thing down here, the handle up here. Handle of the bell. Can you see the handle of the bell here? And then you got your little dinger donger thing down here that clangs back and forth. Okay, so they call these bell curves. And that's what a lot of grading used to be back many, many years ago. The whole class was against each other. Okay, so you would go in. My very, very first college lecture ever sat in on. Walked in, this naive, scared little freshman walking in. The guy walks in, good morning. And he draws this big bell curve on the board and he goes, 1, 1. He goes, 2, 2. He says, the rust. And then he goes, A, F. I don't know why that didn't stay. My A won't stay. And then he goes B, D, C. Welcome to zoology. Proudest B I ever got in my life. Because that meant out of all like 40, there were like 40 of us in there that started that class. Only one person was going to get an A at the end of the semester. Only 2 people were going to get Bs. Like you didn't have, yeah. That was a bell curve. It was awful. But the average ended up being in a C.
I wonder why.
It was bad. I mean, it was very competitive and yeah. I was very proud of that B. All right. Oh, no, it's zoology. Oh, yeah, he made that very clear too. It's not zoology, it's zoology.
Yeah.
All right. Temperature of the first gas here is going to be greater than the temperature of the second gas. The mass is the same, but the velocity is going to differ. So this one is higher temperature here versus here. Okay. And you can see that. Can you see the little tails coming off of here? They're showing you that this one is going faster than this guy because these tails right here are smaller on this one. Okay. So his temperature is greater than his temperature. Okay. Now down here, we end up having the same velocity. Okay. Because this guy, the mass differs, the velocity is the same, but there's a difference in kinetic energy. Okay. So they're showing you with these lines that the velocity is the same. Why is this kinetic energy higher than this kinetic energy?
More mass.
More mass. Remember, kinetic energy equals 1/2 mv squared. So if this is the same, but this is greater in one of them, this is going to end up being greater. That makes sense? Good. All right. Formula for calculating kinetic energy then. We've got our M is mass. We talked about velocity. Kinetic energy then is calculated in joules because energy is always measured in joules. If you've had your physics, you know that. If you haven't, it's in joules. We talked about joules back in the day, though, in chemistry when we did the frequency and wavelength. So you've had some experience with it before. And if you look at your formula sheet, it says kinetic energy here as kinetic energy. Do they tell you what units in? I guess they don't. Yeah, they don't tell you on here what that's in. That's unfortunate. Yeah. They don't say that on the formula sheet. Okay. Rate of effusion then. Effusion is through a tiny hole, like if you get a nail in your tire, your gas is going to fuse through that. Okay. This is Graham's law. You're not going to have to do that one. That one's not on your formula sheet. But we can see that as the particle size increases, the rate of effusion decreases. It's not moving as fast because it has more mass, and it's harder to get through that tiny little hole. So, all right, we are given a sample here of H2, HCl, and Cl2 at the same temperature. Place the particles in order of decreasing speed. So they're going to be slower here and faster here. What's this going to come down to? They're at the same temperature, so their velocity is going to be equal. Okay, so what's the difference between those three things?
Their size.
Their size, okay? So which one of these is the biggest?
CL2.
Cl2, okay? And if you look at the molecular mass of Cl2, it's what? Okay, how about HCl? That's going to come next, right? Its molecular mass is 36.5. And H2, molecular mass is 2.0. All right. We're considering equimolar. What's equa mean? Equal. Okay. Equimolar. So that means that it has the same number of moles. So you want to imagine each one. We got 1 mole of each of these things. Okay. They are placed into a container. There's a little pin opening. After some time has passed, some of the gases, in order of increasing amount remaining in the container. So which one of these is going to stay in the container, more of it? And what's that based on?
Yeah, fluorine is based on size.
Right, it's based on size. So F2 is going to be bigger than
H2. And with the other two, I guess.
H2 is going to be here. More of that's going to be gone, and N2 will be here. After some time is placed, place the gases in order of increasing amount remaining. So the F2 should stay in there longer. Yeah. Okay. Right? My answer key says different, though. So now I'm starting to question myself.
Isn't fluorine smaller because it has more protons?
Why can't things just be easy in life, you guys? Like, seriously. Now I'm like, well, now it's kinetic energy, so it's heavier, so maybe more of it goes out. Yeah, and I can't even get stuff to come up on here the way I want it to. 3, 5.
Well, it's based off increasing, so when you start with the smallest one.
So we will go out to people that are smarter than I. Read the questions. I think it's because the fluorine's heavier, so it has more kinetic energy, more that's going to go out. So what did she say?
Go faster.
Okay. And that's out. Remaining. Okay, I just had it backwards written down. My logic was sound. Increasing remaining. Oh, so the most remaining would be the F2. And we're increasing remaining. So that's how much is left. N2 and then H2. Good?
Yep.
Okay. Okay, deviations from ideal gas law. So ideal gas law says that our particles are going to spread as far away from each other as they possibly can. And we're also going to have a situation where we have no intermolecular forces between them. But that doesn't always happen, okay? And where we start to deviate and move, deviate means to move away from, okay? So where we start to deviate and move away from that ideal gas law is when we are under, one thing is under high pressure, okay? If you think about that, if you think, Oh, piece of junk. I hate this thing. There. If you think about it, if you press down on these gases and increase their pressure, right, that's going to shove them close together. If they get shoved closer together, then the chances of that intermolecular force working again is increased. So high pressure is one of those places where that will happen. The other place, do you think this is going to change? Thank you, finally. Under low temp is another place that that's going to happen. Because if you think about the motion of these molecules, they're moving around. The faster they are, the harder it is for them to kind of hook up. Okay. Low pressure, though, they're moving slower. And so it's a better chance of them connecting with the intermolecular force. That makes sense? If you kind of visualize that. So those are the two situations. All right, we've got 10 ATM and 100 Kelvin. It's going to deviate from the predicted volume based on the ideal gas law. If radon has a smaller volume than predicted, propose a justification for this observation. Well, smaller volume means that those particles are going to be closer together, right? If they're closer together, then there's a chance that those intermolecular forces are going to come back into play. Okay. So if radon has a smaller volume, it is because the IMF is strong. It's going to pull those particles together, and it's going to decrease the volume. If radon has a smaller volume, it's because the IMF is strong. Okay. Okay, good. You guys can still read cursive? There's going to come a point where that isn't the case because they stopped teaching cursive. So then I need to know when that is, you know. I don't remember what year that was, and eventually those kids are going to catch up to me, and then I won't be able to write in cursive.
I think it was like 2 years after us they started.
Okay, so I got another. Oh yeah.
So next year.
Well, this year for some of them, I got a few freshmen every year. All right. Sample 1, sample 2. They're at 298 Kelvin. We're going to identify the gas that's more likely to deviate or be less ideal. Which one's going to be less ideal? Sample 2. Why? Right. There's more volume there. There's more material in there. So there's more chances of them coming together and being able to kind of hook up, and IMF's working. Now, one thing about your test the other day, we had one question on there where they just asked for the answer and they didn't say anything about justify. If they say that, you write down sample 2 and you move. Okay? You don't give a justification on your test unless they ask for one. Or if they ask you to explain, you explain it. Okay? But if they just ask for a question, just a one-word answer, you give that one word and you move. Okay? Keep that in mind. All right. You have time to, I believe that was it in here, right? Yeah. Yep. So you have time to work on your pre-lab because that is due tomorrow.
The juniors run it inconsistently. That's okay. I forgot to text Kate. We just don't know.